It's great to be here talking to you. I don't have this short video of me, so I'll introduce myself in a second. And today I would like to tell you a story about a startup company in the food industry. And the title, well, it's related to it. Excuse me, my bill does not match my order, and it happens, and it happened to the company that I'm telling a story about. The company is obviously fully fictional, but the various elements of the talk are based on real life scenarios and real tears of people involved. If you want to reach me, and I highly encourage to challenge me on my ideas here, that's my Twitter and LinkedIn, and well, I use my first and last name as name of account for basically every service. So if you can't find me in the Ask Everything zone, you can reach me out on Twitter or LinkedIn, and well, on Slido. And a bit of about myself. To kind of look back to a keynote by Christian, I started to design my career at some point. I think it was 5 years into my software career that I started thinking about what I want to do, and started in a domain-driven design community. Spent there a while, then got kind of influenced or excited by the event sourcing that was big back then, and then came to messaging. And then I was hired by a particular software that's a company behind a service bus. And again, looping back to Christian's keynote, I had to figure out a new hobby, because so far software was my hobby, and well, messaging was my hobby. Now I was full-time working for a company that does messaging software, so I had to figure out something as my hobby. So I figured that message delivery and processing will be my hobby. Well, that's kind of related, but to my day job, but it works for me so far. And today I want to tell you a story about a company that wanted to deliver food worldwide. They wanted to disrupt the market for pierogi delivery. And I know that there is a Lithuanian name for this thing, but I can't pronounce it, I'm sorry. And everybody basically here in Central Eastern Europe has a different name for that. Anyway, it all starts obviously with that guy. You have to blame somebody. I could blame Jan, who had the talk before me, for introducing microservices, but he really tried to push back on it. But well, the architect in that company said that you can't just have a monolithic software that you can scale out in an old-fashioned way. Well, you can tell that it's an architectural diagram of that software because it doesn't show you anything about that software, right? You have just boxes, you don't have even arrows. That's the best architectural diagram because it will survive 40 years of evolution of that software, and you don't need to change anything. But that wasn't the architecture that they were going with. They wanted to, well, the architect wanted to make it more complex, so he added more services, and all those services were supposed to communicate in an asynchronous way, because that's what you do these days. So there was a service that was pushing events to a queue or a topic, and then another service picking up those events from that queue or topic, processing them, storing in a database, generating their own events and commands and whatnot, some async messages, and so on. So the chain of services, topics, queues, easy, right? Well, it wasn't that easy. The team early on discovered that the problems related to communicating asynchronously through messages is, I kind of want to process those messages only once. I don't want to send too many pierogi to the customer, or I don't want to build them twice. I want to process my messages, my order messages, exactly once, so that they deliver what they ordered and they pay what they wanted. So that sounded easy to the architect. So the architect threw out of his ivory tower a document that describes how do you process messages exactly once, because he didn't read all the papers that proved otherwise. So you check if you delivered that message, right? That's easy. And if you haven't delivered that message yet to the nth process in a chain, then you process that message and you mark it as delivered, as easy as it is. If a message has been copied and has been delivered twice, then the first step says, check if delivered. Was it delivered? Yes, it was already delivered. Drop the message. Should work, right? But then you try to, well, the team tried to map it on a real-life messaging architecture where they had a broker like Azure Service Bus or SQS if you're on Amazon stack, or any kind of broker, and an application, and they live in two separate processes. So the broker hands off a message, an event, for that matter, to an application does processing and acknowledges, yes, you can remove that message. Because, well, we don't want to remove those messages prior to processing. We don't want to lose the orders because, well, our goal is to disrupt the pierogi delivery market, so we want to deliver each and every order that is placed. And they started to map the architecture document to that infrastructure. And what they started with is, well, first, the broker needs to check if the message has been delivered and mark it as delivered as the end step. So first we check, the broker checks if it's delivered, then the application processes the message and the broker marks is that delivered. The only problem with that approach that they hope to implement is it doesn't really work in real life, and it's not implementable. Why it's not implementable? We need to move back to year 1975 or 78 according to different sources, and have like a short intermediate story about two armies and a castle. So there are two armies that want to take over a castle or a city that is being besieged, and the city defenders are quite formidable. So each army, the left army or the right army, cannot take the city on their own. They need to coordinate somehow to conquer the city. And in order to coordinate, they have to send messengers because they're in the valleys on left and right side of the city. The problem with messengers is that whenever they go besides the city, there is certain chance that they will be shot or they will be killed in other ways, nasty ways, or they will be imprisoned. So you can't be sure that the messenger that you send to the other general actually made it through. And it's been proved time and time again that in messaging systems you cannot actually have a consensus between those generals because, well, you can the easy proof, well, the kind of short proof is that one general sends a messenger to tell the other guy to attack next day in the morning, and then he didn't get any reply, that didn't get any messenger back. And now he is in doubt because he doesn't know if the messenger he sent made it through and the other general knows about the attack next day in the morning, or maybe the messenger didn't get there. So in order to be sure, he would have to request the other general to send back a messenger saying, yes, I got your message. But then that other messenger can also get killed. So no matter how many messengers you sacrifice and send, you cannot reach any kind of consensus. And basically the same situation happens if you try to build that kind of infrastructure that will magically deduplicate your messages. The message broker that sits outside of your process, like SQS or Azure Service Bus, cannot do it for you, even though AWS claims that they have FIFO queues that do deduplication. Well, it doesn't work like that. So you can't have exactly once delivery, no matter what you do in a distributed system. The only thing you can actually do in practice is exactly once processing. So, and that's fair enough. That's usually enough for us because we don't care how many times the message has been delivered or how many messengers were killed. We only care about the result that has happened. So here's the design that is actually implementable. There's a message broker that is any message broker, and the application. And the application needs to make sure that the message, if the message has already been processed, then we don't process it yet another time. So if an order has been delivered and the order message has been duplicated, then we don't deliver that same order again. So it's all about the application, the best way to describe it, as I found on Twitter, was by Victor Klang, that it's not well, exactly once processing as a very clumsy name. A better one is effectively once. That's what we care about. We want our system to behave as the messages are delivered only once, although it can't be achieved in practice. Let's get back to the story about the team that wanted to build that software. That's the user interface that the design people came up with. As you can see, it's very simple. You can add order lines to an order. You can remove them, but you cannot modify them. An order line is an order line, and that means that standard mill size are used. So you get 5 pierogi every time you order. You cannot adjust that, and you cannot have more than one item of the same type. So you can have pierogi with meat and with mushrooms, but you cannot have two items of type meat, because that's the minimum viable product and we don't want to be very complex. And when the software guys, they've seen that user interface design, they said, oh, that's great. That's great for our design, because they spent previous week figuring out how to deduplicate messages. And now when they see the user interface, they realize that the user interface is a solution to their problem. Why? That's because that user interface is a user interface that sits on top of a set, a data structure that you can add items, you can remove items, but you don't have duplicate items in a set. Either something is contained in a set or not. You cannot have two things in a set. Why sets are important? Well, sets are important because operations on sets are proved to be idempotent. So you can apply the same operation on a set twice, and the effect is as you applied it once. You can add something to a set, and then you can add something again to a set, and the result will be exactly the same as you would add that thing once. So that was a great solution for the software guys, and they really like the design team for that. Now, because the code was stored somewhere, we can actually debug the code and see how they progressed when they were designing the solution. And I want to show you a couple of versions of that software, and that's the first version. A little like tour here. What you see on the left hand side, and it will be zoomed in a second, is 3 consoles. The one on top is kind of testing console, where the testing team could type in commands instead of clicking through user interface to test how the software behaves. The red one is the main ordering system, and the green one is some downstream service that receives event notifications published by the red system. And on the right hand side, we'll be debugging the ordering system. So let's see what happens there. That's a single method that processes the add item message, or the command message that adds an item to an order. And it's basically partitioned into four parts. The first part loads the order and then determines if that message has been duplicated. Then there is some business logic, which is adding a new item to the order. Then we save changes to the database, so that's the database commit happening in the green. And then last thing here is publishing an event so that other services in that system can do some processing on their own. So it's item added event here. So let's see how this works. So we kind of submit the first order, and we add some pierogi with meat to that order. And a little bit more description here. So the team here was kind of knowledgeable, and they were aware of various practices in testing. So they were aware of chaos monkey concept. And what they wanted to implement, to be sure, is that their software survives various difficult conditions in production. So they implemented a chaos monkey for their testing environment that duplicated each and every message. So what we will be seeing here is that each message processed will be duplicated. And the other thing that they were aware of is that messaging systems are really good in durably storing messages. So they use a messaging framework that keeps messages durably for them, and if a message processing fails, it will be immediately retried, because, well, that time around it might succeed. So we're adding meat to order ABC, and as I said, that message will get duplicated on the wire. So first time around we process it, we load the state, it's not a duplicate, so we add that order line, we store data in a database, and we publish an event to a downstream system. So far, so good. What happened is that we see in the logs that an item has been added, and also that the immediate retry is going to retry message blah 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 because of the duplicate. What happened is that we actually got 2 copies of that message, and one of them succeeded processing and the other failed because of the constraint in a database. A constraint on 2 columns, the order ID and the type of filling in the pierogi, because you can't have 2 types of the same filling in the same order. So when that duplicate message goes back to the queue because of failure in processing, it's immediately picked up by the messaging framework and processed again. This time around we load the order, we check if we have already pierogi with that filling. Yes, we do have, because we committed our database transaction previously. Then that's a duplicate, right? So we're ignoring that message. And so far the team was happy that they managed to identify a duplicate there. But the problem is that that duplicate didn't result in getting the customers that were early adopters a good experience. The management team, they come to the developer team and said, well, we are hearing complaints of customers that they're not getting what they ordered. They're actually not getting anything, and their credit cards are charged. What's going on, guys? And as good software developers, they said, no, that's not our fault. That can't be our fault, because we have our Chaos Monkey in testing and everything works fine. So it must be something on the business side. Well, the business side insisted that it's not their fault. So the software guys look at it and they figure out, well, they have one condition in their Chaos Monkey that is not covered. They don't simulate broker errors. So they did a change in the Chaos Monkey to simulate broker errors. Whenever you type, you try to add filling to pierogi with meat, with cheese and potatoes, which we call in Poland ruskie pierogi, then it's a failure on the broker side. So let's see what happens. We try to add that type of pierogi here. We process the message. It's not a duplicate yet. We add that filling to our our database object. We store the object in a database. So far, so good. And then we try to publish that event to downstream services. And what happens there is, if it's ruskie, then a broker error happens, because that's our Chaos Monkey simulating the problem. So what happens when we see a problem in processing a message? The message goes back to the queue, right? And then it's picked up again and processed again. So that's the second attempt to process that message. Maybe this time around it will succeed. Well, the problem here is that we already stored our state in a database. We already stored that order line. So when we approach this line of code, it says, well, we have that line item in our order, so that's probably a duplicate. Let's drop that message. And what is happening here is that, well, we have the state, we have an order, we have order line, but the downstream system, be it billing system or shipping system, one of the two, did not receive the item added event. So it doesn't know that an item has been added to the order. So when the customer actually submits that order, in the end, one of these systems, those downstream systems, will not process the order properly. So for the user, the result is message goes to the trash can. So the development team decided that, well, that's probably the fault of first storing the state and then publishing a message. If we store a state and publish a message, then we might get in a situation where we stored our state and didn't publish the message. So the easiest thing that they could do is reverse the order. Let's first publish the message to the downstream systems and then store the state, because that way we will get rid of the problem. And they tried to this approach, and it failed in a different way. So they again tried to change their Chaos Monkey system to detect that error. And this time around, they created a different type of filling for pierogi, which is based on a Swiss cheese. And obviously, everybody knows that you can't add Swiss cheese to pierogi because it's not edible. So there is a validation built into entity framework ORM that checks that situation. So we try to submit an order. Well, that's meat, so that's the happy case. So let's click through it first. and then we try to add Swiss cheese to that order. And what's happening is that we load an order, we check if it's a duplicate. No, it's not a duplicate. So we try to add that filling to our order, and that's so far so good. And we publish the message because we inverted the order here. We're not storing state and then publishing, we're publishing and storing. We publish a message to the downstream system, we try to store the state. So what's happening is the downstream system, as you can see in the bottom of the screen, got that message, the Swiss cheese added to order. The problem is that our ordering system, the main one, refused to store that state because that's a validation error. So what happened here is that the team they actually wanted to build an eventually consistent system where a data change is propagated through events to downstream system. What they have in fact built is a system that is immediately inconsistent because it creates state that never happened in those downstream system. The system that is source of truth for orders, the ordering system, refused to store that state, but yet it published the events that's the node that carry that state change that never happened, which you can see here. And that's called a ghost message, similar to ghost writes in a database. A ghost message is a message that usually an event message that carries a state that never has been persisted to a database in a source system. So to summarize their struggle with messaging and with communication between microservices, they tried publish and then persist data, and then result was ghost messages. And previously they tried to persist and then publish, and the result was that some of those messages that were meant to be delivered to the downstream systems were lost. Well, seems like there is no good solution to that. Well, there is one. There is one that solved it, but first they wanted to figure out what is the problem that they're actually trying to solve there, because clearly that they didn't understand it, and the architect clearly didn't understand it either. So what do we actually want when we are communicating asynchronously between our micro or macro services in an event-driven manner? First, we don't want to lose messages usually. There are certain situations where losing messages is fine, but if you are processing orders from customers and if you want to deliver on your promise to challenge, to disrupt the market of pierogi delivery, you don't want to lose those order messages. That's one. Then there is the idempotence thing. The outcome of processing a message should be the same no matter how many times a message has been delivered or copied in a system. In a distributed system, messages get duplicated all the time. So we don't want to send duplicate orders or to charge people with more money than they ought to be charged. And there's third thing that nobody actually in a team was aware of. We don't want to leak non-durable state through ghost messages. We only want to notify the other parties that something happened if it really has happened and has been durably persisted to some sort of database. And that's the full story, the full problem, the full description of a problem for asynchronous messaging of that sort. And based on that problem description, they were actually quite happy to quickly devise a solution for that. So first, you have to persist the data, the state change that is going to happen if it's not a duplicate. If it's a duplicate, then you don't run the blue step, but if it's not a duplicate, you run the blue step, you persist your state change, so you add the item to the order. And then as a second step, you always publish the resulting messages. No matter if you think it's duplicate or not, you need to publish the downstream messages to the downstream systems, because the duplicate detection might be wrong. If you see a state change in the first step that denotes that it might be a duplicate, then it might be either a duplicate or a sign of a failure that happened after you persisted the change to the database. So that's the only way to ensure that you are effectively once processing messages. And then what happened is, obviously, when they fixed their first problems that they had, the sales started growing exponentially, as in every good startup. So they were getting more money, more developers, everything is great, right? And then the manager comes in and says, well, if you could add quantity to the order line, that would be great. And the development team was, the design team was quite happy to add that because that was easy. The development team was very frightened because adding quantity means that it's no longer a set. So operations on that thing are no longer idempotent by nature. They need to figure out a different way of handling deduplication in their scenario. And they had spent some time thinking hard about it. And what they come up with a different, that user interface preserves a different property. The data structure is not idempotent, but it's immutable in a way that you can add order items here and you can remove them, but you cannot modify them. So with every order item here, there is exactly one or two operations associated. It's either add operation or add and remove operation. There is no edit operation here possible. So if there is already an item, we can associate with the unique ID of a message that created that order item. And this way we can deduplicate it. So let's see how it works in practice. So first we start with our Swiss cheese scenario. We add some Swiss cheese. We check if the message ID here stored along the order item is the same as the message ID of a message that we are currently processing. And here the assumption is that each message has a unique ID, and if a message gets duplicated along the way, the ID gets duplicated too. So all the duplicates carry the same message ID. So if it's not a duplicate, we proceed with creating an order line, we add it, we save the changes, and then we blow up because of the validation. So far, so good. So now let's try something different, some meat. We check the duplication, it's fine. We add the order line and we save the changes. And last thing, we publish an event. Works as we expected. Now let's try to see what happens with the duplicate of that message that failed to be processed first time around, and we reattempt to process them. We check if order lines contain an item with the same ID as message currently processed. And as I mentioned, the duplicates carry the same ID. So I should be able to find an order line that has the same ID associated as my currently processed message. Yeah, that's fine. I detected a duplicate. That's good for me. And then what I'm doing is I'm not returning from that method immediately. I'm publishing the event again. Why? Because I'm not sure if I actually publish it first time around, or I encountered a broker error and didn't manage to publish them. That's good. We can manage to deduplicate those messages in the downstream systems, right? If we figure out how to deduplicate messages in our main service, the ordering service, the downstream services should use the same logic. Well, the only problem here is that, as you can see, those two copies of item added event have different IDs. That violates our assumption that duplicates have carry the same ID. The reason for it is that the message didn't get duplicate along the way in the transport. Most message brokers guarantee that message duplicates have the same ID. This message has been generated twice in that service, and each time around we generated a unique ID, unique GUID that is a brand new GUID. So the downstream system, the developers in that room over there, will have hard time figuring out if that order contains two items with meat, or maybe the only one item with meat. That's for sure not doable based on the message ID. So, well, the problem here is that the messages come from front end to the ordering service, and those are duplicates with the same ID. And then after order service tries to deduplicate them and applies its own logic, it generates messages that are logical duplicates but carry different IDs. Well, what's the solution to it? The solution would be to, well, let's not get ahead of ourselves, because the implementation team, as in most startups, didn't have time to fix all their bugs. There comes a manager and says, well, again, we have requirements change. If you could allow order lines to be updated, edited, that would be great. So that's also a simple change in the UI. For the design team, it will be a great big change for the development team, because now you can have multiple messages associated with each order, and you cannot just assign order line a message ID for a message that created it. So what they did instead is that they created a table in a database called processed messages. And each time they process a message, they apply the business logic, and within the same transaction, database transaction, they insert an item, a row, to the processed messages table. And now, when they want to check if messages duplicate, they just check if the row is already in the processed messages table. So let's see how it works. We open a transaction. We see if processed messages contains a row with the ID of the message. If it doesn't, then we add that row through the object relational mapper here. We ensure that this thing is persisted in a database, and then we actually proceed to invoke the business logic here. And the business logic is invoked as previously, adding a new line item. And last but not least, we need to publish the downstream messages. And what we do here is that change that the team applied in the meantime, because they didn't want to, they did want for the downstream systems to be able to deduplicate their messages. They decided to assign deterministic message IDs to their messages. So even though the downstream team will receive two duplicate item added event, those two copies will have the same ID. So they decided to use some kind of deterministic GUID generator based on the incoming message ID and the name of the service, just to generate the next message ID and set it and publish. That's fine. And when a duplicate comes in, well, the duplicate from the front end, so we're still in the ordering system. What we're going to have here is that we found that the processed messages table contains already a row with that ID. So we set a flag in our processing context to remind us about that, and we execute the business logic. The business logic, what it does is it checks that flag and says, okay, that seems like a duplicate, so I am not going to apply again the business action. So I'm not going to add another copy of an item to the order, but I do need to publish the messages to the downstream systems. And I'm doing it using the same deterministic GUID generator based on the incoming message ID and my service name. So the result here is, after I publish those messages, I don't have a slide for that. Sorry, I didn't move that. The result is that the downstream systems, they see two copies, as I said, of the item added event, but those two copies carry the same deterministic GUID generated each time, the same value. So they are able to use exactly the same algorithm in those downstream systems to deduplicate those messages. So it's good, right? It's effectively once we managed to solve the problem. Well, not really, unless you have unlimited space. Because in order to store the message IDs of all the messages you processed so far, you need unlimited space. Because when do you say, well, I don't need those messages from those message rows from last week? If you happen to get a duplicate that is delayed by a week and a half, you will process it as a brand new message. So I would say it's mostly once. Mostly once is a variant of effectively once when you actually purge the process messages table, and you can do it after a week or month or 2 months. It depends on how sensitive you are to duplicates. Because if you purge that process messages table, if you remove the rows that are older than a month, that means that you cannot detect duplicates that are more than a month apart in time. And that's usually fine for most business applications, but probably not for every application, and not every application will have the same requirements for that. And then what happened is that something that never happens in startup environments, and in fact never happens at all. The manager comes in and says, that's refactoring sprint. We don't want you to touch the code or to change the functionality for next month or so. But if you can just clean it up and make it better, that would be great. And what the lazy developers do when they encounter something like that? Well, they can play foosball or something like that, and they can also use kind of support they have and talk to the messaging vendor, in this case, messaging framework vendor. So to me, for live chat. So, hi there, are there any established patterns for implementing idempotent message handlers? Asked the lazy developer. And you know, lazy developers are good ones because they don't over-engineer stuff. And then somebody on the other side asks, have you tried the outbox? And that's a different approach. Well, that's a slightly modified approach to the one that I talked a second ago. That's a big diagram, but it's easy to read. So what happens with the outbox patterns is that when you process the message, you open a huge big transaction with a messaging queue, and all of them support some sort of transaction or release, and then you receive the message. You deduplicate that message. You check if a message is a duplicate. If it's a duplicate, you don't do anything. If it's not a duplicate, you open another transaction with your data storage. It's called the outbox transaction. Within that transaction, you execute your business logic. So you add order lines and and things like that, and you send messages. But instead, you're not sending those messages actually on the wire. You're storing them in the same database as your business data, in a separate table or something like that. If your database supports separate tables, hopefully it does. So you store those messages, you store your business changes, and you commit it as a unit. So at the end of the orange transaction, you have all the messages with their unique randomly generated IDs stored safely, and you have your business change stored safely. And only then you dispatch those messages to the downstream system. And you can reattempt to dispatch those as many times as you want, because those messages are stored, so they are immutable. The message IDs are even if they were generated non-deterministically in the first place, when they are stored durably in a database, they are not going to change each time you dispatch those messages. And last thing, you commit that queue transaction, so you actually mark that message as processed. If you fail to do the last step, the last green step, the message comes back again, and you check if it's a duplicate or not. If it's a duplicate, well, you just don't execute the business logic, but you do dispatch those messages to the downstream systems, because you cannot be 100% sure if they were dispatched the first time around. So when the team implemented that approach, they got rid of like huge amounts of their code, their infrastructure code, and adopted the ready-made solution to it. So their code looks like this right now. They load the entity from the entity framework. They load the order line. If there is an order line that already exists, they modify it. If it doesn't really exist yet, they add it, and they publish an event. There is no infrastructure and plumbing code here, and that's because what they are doing is they are storing those messages, and they don't need this processed flag anymore. And they don't also need the deterministic message ID generation either. Everything happens here in the console as it used to have. And now, well, there is a different problem. Well, after the refactoring sprint, the manager comes back yet again, and they hate him already, and says, well, okay, you solved all the deduplication problems, that's great, but now we've seen that those messages sometimes are processed in the wrong order. Can you do something about it? And that's a story for a completely different talk, unfortunately. But if you want to learn something more about using process manager pattern to handle out-of-order delivery that happens every time in distributed systems, that's a code that you can access some videos for that. So you can, I'll be tweeting that code also, so you don't have to take a picture. If you want to, you can. And well, that's the time for questions. Thank you very much.